Hey everyone, Katrina here, and today we're going to talk about how to quickly do implicit differentiation. Be sure to subscribe for more videos like these. Okay, so I just released a full crash course on implicit differentiation, so be sure to check that one out if you want a full step-by-step guide. Today, we're just going to be considering an example, and we're going to be doing it fast. So just really quickly, right off the bat, we use implicit differentiation when we don't have some term y equals to f of x. So when this is not available. Instead, we have y integrated within our function. So because of that, we treat y as kind of like a variable within our function that we're differentiating, but then we also have to apply chain rule to the y when we differentiate it. So let's just look at a quick example here. So what if we have x squared plus, or let's say 5x squared plus y cubed equals to 1. So in this case, we don't have y isolated on one side of the equation, so we're going to have to use implicit differentiation. Technically, you could go about and do the algebraic manipulation first for this one, but for the purpose of this example, I'm going to show you how to use implicit differentiation directly to this equation. Okay, let's begin. So the first thing that we have to do is we need to differentiate both sides of the equation. Okay, so what does that give us here? We have d over dx of 5x squared plus y cubed equals to d over dx of 1. Awesome. So following derivative rules, we can technically, because we have an addition here, we can apply this derivative to both these terms individually. Meaning we've now got d over dx of 5x squared plus d of dx of y cubed equals to d of dx of 1. Okay? So our first term over here is just in terms of x, so y is not present, so we're going to differentiate as normal. Again, I have other videos on just regular differentiation, so be sure to check those out. So here we're going to use the power rule. So all we have to do there is bring down the power. So we have 5 times 2, x to the 2 minus 1 by power rule. And now for a second term, this is where things get a little bit different because it's y. On the outside, we're going to treat it the same. So we're going to start using power rule. So we've got 3 times y to the 3 minus 1 by power rule. But now what's different is because y is technically our dependent variable here, we have to then multiply this whole term by dy over dx. And that's the only thing you have to remember for this. Whenever you're implicitly differentiating and you're trying to differentiate y, you have to use the chain rule here. And all you have to do is apply normal derivative rules to y, and then simply just multiply your answer by dy over dx for that term. That is all, okay? And then now on our right-hand side, we're taking the derivative of a constant, so that equals to 0. Okay, so let's move on here. So we've got 10x to the power of 1 plus 3y to the power of 2, and then we're just going to say dy over dx, we'll write that as y prime, and that equals to 0. The next step we have to do here is just, we want to isolate for y prime, because that is our goal. We want to find what is the derivative of y with respect to x. So we'll just do some algebraic manipulation. So we got 3y squared y prime equals to negative 10x, because we moved this term to the other side. And now we're going to divide both sides of the equation by 3y squared. And what does that give us? So that gives us our y prime isolated on this side, which equals to negative 10x over 3y squared. And just so you know, there's an alternative notation. You can also write this as dy over dx, which is Leibniz notation, which states that we're taking the derivative of y, our function, with respect to x. And that is simply negative 10x over 3y squared. And that, my friend, is the answer. And I just showed you how we can use implicit differentiation to solve for functions where y is not explicitly defined, where it is not isolated explicitly on one side of the equation. Again, for more information, be sure to check out my previous crash course on implicit differentiation. And I really hope this is a tool you can now add to your differentiation toolkit. And I hope you enjoyed the video. Please give it a like and definitely subscribe to continue on this fun and exciting math journey together. And with that, I'll see you next time.